So happy about this. I'm just going to say again, welcome everyone to the first more or less in-person cosmology lunch since March 2020. We're super happy to have Adam Broussard from Rutgers today. He's doing his PhD and finishing up actually this year. And he's working with Eric Weiser, who is actually also joining us today. And so I think, unless there's anything from any of you, I would say, without further ado, please take it away, Adam. And thank you so much for visiting.
Of course. Thank you very much for the introduction, Andrina. And I'm honored to be here for the new first in-person meeting. I feel like I'm regretting now that I didn't put an image of my face on my first slide, so you can all see what I look like without a mask. But alas, that's how it goes. So as Andrea mentioned, I'm a 6th-year graduate student working with Professor Eric Weiser, and I'm really delighted to be able to attend today and to share with you some of my recent research, which focuses on selecting galaxies with accurate photometric redshifts using a neural network classifier. So the idea behind this research project is that galaxy clustering, which is oftentimes just called large-scale structure, is a very powerful cosmological probe, and it probes the dark energy equation of state and can be used to probe the evolution of dark energy over time. But typically, although you might want to do a 3-dimensional clustering analysis, this is not possible without spectroscopic redshifts that give us very, very precise distances to galaxies. So instead, what astronomers typically have to resort to is a photometric redshift analysis, or photo-Z. And this is done in tomographic redshift bins, where within each bin, an angular clustering analysis is done instead. And the Vera C. Rubin Observatory's legacy survey of space and time is really unique in that it's going to provide photometric redshifts for billions of galaxies, which means that we can actually, it allows us to consider some very different selection methods, such as rejecting half or even more of the total sample of galaxies in an effort to get really, really accurate photo-Zs, because there's such a large catalog of galaxies that we won't come up against the shot noise limit, and we'll discuss that a little bit later. The thrust of this particular analysis is that we train a neural network to essentially reject galaxies that have inaccurate photo-Zs in an effort to improve our cosmological measurements from the galaxy sample. To give you an idea of what some common photometric redshift fitting codes are and how they work, photometric redshift fitting codes can broadly be discriminated based on being machine learning based or template based. Some examples of machine learning based algorithms are trees for photo-Z, or ANNZ, or NetZ. Trees for photo-Z is a random forest algorithm. These other two are neural networks. The first one is just an artificial neural network, and the second is a convolutional neural network. And then, on the other hand, we have template-based methods, which have typically less clever names, I guess, than the more recent machine learning-based methods. But so an example of that one would be something like EZ by Gabriel Brammer, and these essentially rely on a template library that they will calculate photometry for in your particular filters across a grid of redshift, and then they compare the calculated photometry to the observed photometry and minimize the chi-squared to figure out what your best fit redshift is. So these each have their own strengths and weaknesses that kind of go with what the typical weaknesses of a machine learning based method are, like not matching up your training and test samples and things like that. So we can pause for a second and kind of look at what really makes photoz's difficult or easy to determine. And I have a simple example here where I show a relatively blue galaxy spectrum in blue and a relatively red galaxy spectrum in red. And it's really evident here that if all you had to work with were the circular points that are plotted there, which represent the photometry of the underlying spectrum, the blue spectrum is really quite hard to place in redshift. You can't really determine what its redshift is very easily compared to the red spectrum, which has a very clear break around 4,000, 5,000 angstroms here, and a photometric redshift fitting software will be able to easily key in on a broad feature like that to give you a very accurate redshift. So just different spectral types will essentially lead to different inherent uncertainties in PhotoZ. Our PhotoZ pipeline essentially has two steps, where in the first step, we perform an initial photometric redshift fit using trees for PhotoZ. As I mentioned, that's a random forest algorithm. Our particular choice of PhotoZ code here doesn't really matter. We chose TPZ because it has relatively good systematics based on a paper produced by Sam Schmidt in collaboration with the Dark Energy Science Collaboration, where they studied many different PhotoZ codes, and so we just chose this one out of them because it had good results. But the second part is really our addition to this analysis, which is that we, using those initial photometric redshift fits, we then pass all of that information to a neural network classifier, which outputs the confidence that a particular galaxy is within delta z over 1 plus z of less than 0.1. And that particular value of 0.1 is not an accident. We'll talk a little bit later about how we chose that value. But essentially, it's trying to select galaxies that have true redshifts that are very close to their photometric redshifts. The features that we train on are summarized here. This top section shows features that are used by both TPZ and the neural network classifier, or NNC. You'll see it includes magnitudes and colors, which you're probably familiar with. And then a third one that we call band triplets. These are differences of adjacent colors. So in the same way that a color essentially traces the logarithmic slope of a galaxy spectrum, a band triplet traces something like the second derivative. It kind of measures the peakiness or the dippiness of those three bands.
So those are three different quantities, or those three numbers taken together? You put
so this is one quantity right here. G minus R minus I is one band triplet.
So that's just G minus I.
It's not G minus I because of the minus sign here. So it's actually G minus 2R plus I.
Sorry,
yeah.
I can't do arithmetic.
That's okay. It's easy to get turned around on, right? Because it's a lot of letters. But yeah, so that essentially measures how much the middle band sticks up or drops relative to its neighbors. And then after TPZ is trained on this set of features, we add in its summary statistics for each galaxy to the list of features that are used to train the NNC. And so those are the photometric redshift, which is ZTPZ, the photometric redshift uncertainty, and then this parameter here called zconf, which is a measure of the Gaussianity of the photometric redshift probability distribution function, which is its essentially the posterior distribution. So to give you a better idea of zconf, since that one is probably the least well-known of those three parameters, this shows a measurement of zconf for 4 different galaxies. The true redshift is plotted as a dot or a dashed line in each of these. And you'll see I've noted at the bottom that zconf is the PDF integrated over the photometric redshift plus or minus its uncertainty times 1 plus z. And so this gray shaded region shows the integration of zconf for each of these. And you can see how essentially the PhotoZ estimate is in the middle of that gray region. And you can see how as the PhotoZ PDF becomes more peaky, your zconf value approaches 1. The neural network architecture that we use is a deep neural network with 4 hidden layers. These have an activation function, which is a SALU activation or a scaled exponential linear unit activation function. The reason for this is because a neural networks will be what's known as self-normalizing with a particular with this particular activation function and initialization distribution. And essentially what that means, if you're familiar with neural networks, is that there's an issue with neural networks sometimes causing neurons to die out, where their weights become very small and they never recover, or where neurons will essentially dominate the fit and their weights become very large relative to their neighbors, and essentially one feature will dominate your fit. And a self-normalizing neural network keeps all of the weights of the neurons at each layer Gaussian distributed, so you don't end up with a bunch of neurons that are dying off or just a few neurons that are dominating the fit either. And then finally, yes, go ahead.
Can I just ask, did you find that to be superior to ordinary value plus a batch normalization, or something that is effectively basically preventing the same problem from occurring?
Yeah, so I found a slight increase in performance. It wasn't great. I think that I think that that's typical of SALU as well. Is that I think you see maybe a very small increase in performance, but I think that one of the primary benefits is actually a decrease in training time, which we did not particularly have a problem with, but that is one of its primary benefits.
All right, thanks.
Yeah.
I mean, sometimes it is the right answer to give certain inputs low weight because they turn out to be not useful.
Yes.
But you're saying sometimes this gets pathological, or
right. So essentially, when you're training your neural network, it's going to be measuring your loss function by feeding your data forward through the network, and then it does a pass back where it computes the partial derivatives, essentially how to adjust all of the weights to move closer to a minimized loss function. And if the weight becomes something ridiculously small, like 10 to the minus 10, then the gradient is also very small for that particular value, and then it essentially never recovers. It never pulls the weight out of that tiny value. And then finally, the output layer has a sigmoid activation function, which just essentially produces values from 0 to 1, where 0 is going to be galaxies with very low confidence of an accurate redshift, and 1 is very high confidence of an accurate redshift. All right, so I mentioned earlier that we're going to come back to that delta z over 1 plus z of 0.1, and this is the slide. So here I have plotted on the y-axis the fraction of the sample retained, and on the x-axis the neural network training boundary of delta z over 1 plus z. And these different curves that I've plotted in each panel are the values of the particular statistic that's at the top right. So the outlier fraction in the left panel, the normalized median absolute deviation in the middle panel, and then the standard deviation of the photo z error in the right panel. And essentially we're looking for a solution where the sample size is maximized for a given value of each of these parameters. And you can see that in the left and the right panels, this happens around 0.12 or so. That's 0.1 or 0.12 is about where the outlier fraction and the standard deviation are optimized relative to the sample fraction. But for the normalized median absolute deviation in the middle, if you draw a line of constant sample fraction across that middle panel, you're actually increasing the INMAD as you increase your neural network training boundary. So to kind of balance these two effects, where the left and right panels have an optimization at about 0.12, but this one gets worse, and the middle one gets worse as you go to a higher NNC training boundary, we bump it back a little bit to 0.1 to be essentially our optimal value of delta z over 1 plus z to train for our classifier. All right, now we can talk a little bit about the data sets that we used for this particular analysis. I've named each of them, and the reason for that is because we're going to refer to them a lot, and it just helps to keep in mind what's what. So the data set that I'll refer to as HSC spec is just all of the HyperPrimeCam PDR2 wide field galaxies that have spectroscopic redshifts and photometry. So this is just galaxies that we know the truth for. HSC Phot is a random subsampling of HSC PDR2 wide field galaxies with photo-Z's. So these are galaxies that we have we can get a photo-Z for, but we don't know the truth. And then finally, Cosmos 2015 is a survey that was done in the Cosmos field that includes a lot of medium band filters as well. And so this is this survey is known for its high quality photometric redshifts because they have about 30 bands that go into these photometric redshifts. So if you're optimistic, then these are spectroscopic like photo-Z's, and if you're pessimistic, they're just really good photo-Z's. And so we actually will treat these as true redshifts for part of our analysis because this can kind of act as an intermediary between HSC spec and HSC Phot, because we don't know the truth for HSC Phot, but we can get truth from these Cosmos 2015 redshifts. And I'll explain that more as we get to it. So this is a plot of the Cosmos 2015 photometric redshifts versus their spectroscopic redshifts for galaxies that have them in HSC. And you can see that, it's not perfect, but even though these Cosmos 2015 redshifts aren't spectroscopic redshifts, they really only add a modest scatter to the sample if we treat them as truth, because the outlier fraction is about 4%. The normalized median absolute deviation is 0.014, and the standard deviation is 0.074. So it's very tight. It may not look quite like it on this particular plot because the color bar is log normalized, but it's actually very, very dense in that one-to-one core region, which is great. And we can talk a little bit about how this small amount of scatter may affect our results as well in the later part of the slides. Yes, sir.
If you have the spec C to make this plot, why didn't you just use that as a truth table?
So we don't have spec Z's for all of the Cosmos 2015 galaxies. We just wanted to see, what is the inherent scatter in the Cosmos 2015 photo Z's, basically. Yeah. All right. So here you can actually see the difference essentially in feature space between these several different data sets. So on the left side, I have the HSC spec sample in I versus G minus Z color. In the middle is HSC Phot, and on the right is Cosmos 2015. And you can see this dark blue edge at the bottom right of HSC spec. This is caused by the preference for bright red galaxies in these spectroscopic surveys. And obviously this distribution is much more, has many more features than the ones on the right. HSC Phot reaches to a somewhat dimmer limit at the top, and then Cosmos 2015 is kind of an in-between of the two, but these are galaxies for which we know true redshifts, and so that's going to be helpful for evaluating how well we think we would perform on a data set like HSC Phot.
Actually, this just brings up a question. You're pushing to faint enough magnitudes that you start worrying about the photometric errors on the HSC side.
Mm-hmm.
Did you, in your various training, did you put the estimated errors in as something that you want to look at?
Yeah, so I did try inputting the photometric uncertainties and the uncertainties in colors and band triplets and things like that as features. And we found that it really didn't have much of an impact on the fits. All right. So we consider 4 different cases of training set and test set pairs. And each of those is kind of instructive of it teaches us different elements of what we would want to know about these data sets and kind of culminates in our final analysis. So the first the first case is training and testing on HSC spec. And the idea here is that this is an idealistic case, but it kind of shows what our best case scenario is if we train on galaxies with truth and we test on galaxies with truth. The second case actually approximates the training and testing mismatch if we were to try something like train on HSC spec and fit on HSC Phot, because we're now training on HSC spec and testing on Cosmos 2015 here. And then case 3, we actually train and test on Cosmos 2015. So this is where we actually get to get a picture of what is the scatter that we expect in our results from the imperfect photoz's of Cosmos 2015. And then finally, case 4, this is our most sophisticated case, where we actually construct a training sample using data augmentation to try to make it look as much like our test sample as we can, while keeping the true redshifts. And that this is, hopefully that gives us the best result, essentially. And I'll go through each one of these one at a time now in more detail. All right, so here is case 1. So training on HSC spec and testing on HSC spec. You can see this. So we're going to go through several slides that have this same figure set up. So this is the color magnitude diagram that you saw earlier on the left, so you can reference it. On the right, and since the test and training sample are the same, there's only one. On the right, this leftmost panel is the initial photometric redshift fits. So what does it look like immediately after it pops out of TPZ? And then the right 3 panels show what results we get if we select down to 1/3, the best 1/3 of those galaxies using 3 different criteria. So this left one here is if we select based on the photo-Z error standard deviation. The middle one is if we select based on Z-conf, and then the right one is if we select based on the neural network. So we'll keep an eye on this right panel because that one's going to be the one that corresponds to our method. And these other ones are if you just made similar cuts using the reported statistics from TPZ. So
you may be about to show this to us, but I'd love to see where the objects that you selected lie in color magnitude space.
I don't have a plot of that. I may be able to dig one up actually after the talk, but it's actually a very complex selection in color magnitude space. We've looked at it. I just don't have it in this particular slide deck. But there are many different sub-regions within this plot that it selects out as the accurate galaxies to start with. It's really interesting to look at, so I can show you that maybe in the time after. So here you can see this resulting population is great. It's almost on the 1-to-1 line. There are very few outliers. Life is good, but this is the idealistic case, as we said. This shows our best case scenario if we had truth for both. The next case, this is if we had a realistic mismatch between our training and test sets. So if we were to train on HSC spec and fit HSC Phot or something like that. So here we have our color magnitude diagrams on the left, and you can see that the redshift fits have worsened considerably, as have the selections, but the selections actually do make a really significant improvement to this fit on the left, where you can see that the outlier fraction across the board is greatly reduced. The INMAD is greatly reduced, sigma is greatly reduced, and in particular, they're reduced the most by our method on the right, this neural network classifier. We essentially get the same INMAD as for these other methods of selecting, but we get a better rejection of outliers, which is going to be important for our cosmological analysis, as we'll show a little bit later as well. Yeah.
Why did you choose 0.9 here for the threshold? And what does that distribution look like of the CNNC or CNN?
Yeah, so that's basically the neural network confidence value. So the reason we chose 0.9 here is actually all of these values have been chosen such that they select the same number of galaxies, and it's 1/3 of the original sample. So these are all the same sample size, and they're all the best 1/3 essentially. So that was just chosen based on whatever the value was that we needed to get that number of galaxies.
And the third just seemed like a sensible number. Yeah, pulling that, decided to use it.
That's a fiducial example, but we'll do some we'll show how you can actually tune this to get any sample fraction that you want a little bit later. Yeah. But as far as the distribution of C and NC goes, it's relatively flat. It's not perfectly flat. In reality, the actual value of C and NC is not terribly important. We really just use it as a way to select a certain fraction of the sample. There's no physical meaning to that value, really. It's not a probability or anything. Okay, so this third one, this is another idealistic scenario, but this is where we're training and testing on Cosmos 2015. And you can see that our redshifts have improved considerably, but it's not quite as good as that first case that we saw, because there's some inherent scatter in the Cosmos 2015 photoz's. So this is just instructive for seeing kind of how much scatter are we left over with after training and testing on Cosmos 2015, and we'll actually come back to that in just a second. And then this final one, I'm going to actually spend a couple of slides on because it's a bit more complex. So this relies on the assumption of scalable galaxy SEDs, that you can renormalize a galaxy's SED and its redshift doesn't change. And the idea here is that for each Cosmos 2015 galaxy, we essentially treat that galaxy's SED as a 5-dimensional vector, and we normalize it to 1. And then we do the same for all of the HSC spec galaxies, and we compute dot products to see which one has the largest dot product, meaning they have the most similar SED shape. Then we renormalize this HSC spec SED that matched our first galaxy, so that now its SED has the same normalization as the first one, but we keep its spectroscopic redshift and we add noise if needed. So now we essentially end up with a galaxy that has a very similar SED to our starting galaxy, but has a known redshift, as a known spec Z. And you can see the color magnitude distributions here on the left, where essentially they look identical. We've produced a color magnitude distribution from a spectroscopic sample that looks almost exactly like the one that's going to be our test sample, but we know truth for this left side from spectroscopic redshifts, which is great. What's an SED again? So SED stands for spectral energy distribution. I'm glad you asked. I should probably add that as a written out word so that people don't skip over it. But that's just essentially the amount of light that a galaxy emits across a range of wavelengths. So in our case, the SED is, we're working with 5 bands, GRIZY, and the SED is the 5 flux densities that we get for each of those filters. Good question. All right. So in our particular case, we have the benefit of a spectroscopic sample that actually goes quite dim. It wasn't quite as broad in color at the dim end as the photometric sample, but it turns out that it actually does a pretty good job of representing even dim galaxies. So we will end up not seeing a very big benefit from this particular data augmentation step, but this could be helpful, we think, for other surveys for which have much more limited spectroscopic coverage for their training samples. And here is the result of that. So here you can see our photoz's are back to looking okay. But after our selection, the outlier fraction is reduced almost by a factor of 5, or probably about a factor of 4. The NMAD is reduced by a factor of 2, and the standard deviation is reduced by a factor of 2 as well. And that our neural network classifier in this right panel actually really outperforms all of these, the uncertainty cut or the Gaussian cut across the board. So essentially we are able to show that our neural network does a better job of selecting galaxies with accurate photoz's and rejecting outliers in particular than even doing a more simple cut based on just a reported statistic. So it's important to note here, I've actually essentially just cut out that right panel here, and now I've added in the Cosmos 2015 plot that we saw earlier. And now you can see that the outlier fraction, the NMAD, and standard deviation are actually pretty comparable between these two sets. The NMAD is not as much so because it's very, very tight for Cosmos 2015. But because we are doing fits with TPZ, which is a random forest algorithm, and the Cosmos 2015 photo-Z fits are based on a template-based code called Classifier, then it's not unreasonable to say that many of our outliers and many of the outliers that are produced by our fits are not the same as the outliers that are produced by a Cosmos 2015 fit. So we can't really quantify exactly what fraction of our outliers are in common or different between these two, but it's not unreasonable to say that a good fraction of them may not be in common between the two. So that essentially our results are actually even better than what we report, and a lot of the scatter may just be due to scatter in the Cosmos 2015 photo-Zs.
I'm not completely convinced of that, but I guess, I mean, ultimately, this is a question that I suspect will come up again is just understanding where those outliers lie in color space, what type of galaxies you're looking at, and so on. But we'll let you go.
Yeah, so this isn't necessarily intended to be convincing. I would say that it's statistically suggestive, but it's not a hard result that we have. Yeah. All right. So I've been showing you plots that demonstrate cutting out the best 1/3 essentially of galaxies from each sample. In this plot, we show that you can actually tune your sample to produce any sample fraction. So I have the sample fraction plotted on the y-axis versus each of our 3 metrics of accuracy on the x-axis. The curves that are traced out by the reported TPZ statistics are shown in gray and in black for zconf and the standard deviation for zconf and the uncertainty in gray and black respectively. And then our results from the neural network classifier are shown in blue. And here, being up is better because you want more of your fraction of the sample to be included in your selection. And being to the left is better because you want to minimize all of these statistics. You want the smallest outlier fraction, the smallest NMAD, the smallest standard deviation. And so here you can actually see that this is why the neural network classifier was outperforming those other methods in those other plots, is because the blue curve lies above the gray and black curves for almost the entire range of sample fractions, but particularly when you're selecting down to less than half of the sample. And you'll see that it actually lies a little bit below on the NMAD. So it essentially, you're sacrificing a very small amount of NMAD increase by using this method for a very big decrease in your outlier fraction or your standard deviation of the photo-Z fit. All right, what about other photo-Z codes? So one other code that we tried this on was BPZ, or Bayesian Photometric Redshifts, which is a template-based Bayesian photo-Z code. And I've added the curves for BPZ here, where the selection using the BPZ uncertainties is shown as a light red, and then the neural network that was trained on BPZ is shown in dark red. And you can see that BPZ doesn't perform as well as TPZ, even in the initial redshift cuts. Matter of fact, it does actually a pretty bad job once you get down to less than half of the sample of actually improving the sample statistics if you just keep picking out galaxies with lower and lower uncertainties. But the neural network classifier is able to do a really good job of actually improving this sample, especially for small small selected samples, just not as good as the TPZ version due to the presumably the decreased photo Z quality. All right. Just to give you an idea of our model validation, the here I've plotted, this is a similar plot to what you've seen already, but on the x-axis here, now this is the training sample size, and on the y-axis is the sample fraction. And again, each of these curves corresponds to a different value of the particular descriptive statistic in its plot, in its panel. And you can see that we essentially stop making improvements to the outlier fraction and the photo Z error after 40,000, 50,000 objects, and but that we are continuously improving the InMat, but only barely, which is essentially indicated by these wide, the wide spacings. So if you draw again a horizontal line across, you're barely decreasing your InMat as you go to higher training sample sizes, and you get basically no benefit out of the outlier fraction or the standard deviation. What does the redshift distribution look like? So it's not, it definitely isn't a uniform selection in redshift, but it does have enough galaxies across the full redshift of our sample that we can do a tomographic analysis on it. So, so here, this is just the sample, the fraction of the sample in each of the, on the y-axis across the redshift of the sample. And then these colored lines correspond to different values of CN and C, which was the neural network confidence value. So if you make different cuts, essentially what fraction of the sample are you left with as a function of redshift? All right, so now what about cosmology, right? Everybody cares about cosmology here. So the big idea with one of these cosmological analyses is that there are kind of three big factors that you have to consider when you are trying to maximize your signal to noise. And they are the shot noise, your bin contamination, and the bin number. The shot noise is essentially Poisson noise that comes about as a result of the fact that you're discretely sampling a smooth underlying density distribution. So there's some smooth function of matter throughout the universe, and we're measuring points of it, which are from these galaxies that have been drawn from this distribution. And if you don't have enough galaxies to essentially measure that distribution, then that Poisson noise that gets introduced is the shot noise. So here it doesn't show up quite as well on the screen, but this is just a redshift survey where each galaxy is plotted as a point, and you can see that if I took out 3/4 of the points, it would be much more difficult to measure the underlying structure. Second is bin contamination. So here I have plotted the galaxy's true redshift versus where it essentially gets which redshift bin it gets assigned to. So if we knew perfectly the redshifts of each of these galaxies, these would all be nice, well-contained bins within these gray lines. But because there's uncertainty in the photometric redshifts, they kind of spill over into their neighbors. And there are two different types of issues here. The first is that galaxies can get assigned to the wrong redshift bin just due to photo Z uncertainties that scatter the galaxy across the boundary. So if it's near a bin boundary and it doesn't have a very, very precise redshift, then it might just scatter across, and that's essentially this tail that you see at the, I'm referencing this blue curve here, but that's that low tail that you get as it enters the next neighboring bin. And then these have a relatively small impact per galaxy on your cosmological measurements, because there's some correlation between these two bins in terms of their that matter distribution, but there's a lot of them. On the other hand, wide outliers are caused by completely wrong redshifts, where you just assign a galaxy to a ridiculously wrong redshift, like this small tail over here. There typically aren't very many of those, but they can cause actually much larger problems on a per galaxy basis, because this kind of stuff is completely uncorrelated from your matter density distribution that's at low redshift, and it's essentially noise that gets added into your signal. Yeah.
Well, the first effect only matter as much in bins that are not along the edges, because I would imagine in the center bins, it's equally likely to go left or right. But a bin on the edge, it's more likely to.
That's a good point. So, you know, in this blue bin, you can't scatter lower than 0, right? So it's a different effect for bins that are in the middle versus bins that are, at very, very low redshift. All right. Yeah, okay. And then finally, the number of tomographic redshift bins. So the idea here is that you want to have as many bins as possible, because the more bins you have, the narrower your bins will be, and they produce a better, essentially two-dimensional cross-section of this three-dimensional matter density field, and we get a much more accurate look at what that matter density field looks like. The downside is that, as you can see from these, you get some mixing of bins when you have very few bins, but you get much, much more mixing of bins when you have a lot of them, because as your bin sizes shrink, that contamination goes up, because now your bin sizes are near the size of your photometric redshift uncertainties, and so you get a much higher contamination fraction. Also, as your bin size shrinks, you run into the shot noise limit, because you now don't have enough galaxies in your bin to get a good measurement. So this is the balancing act that we have to do. And one thing that's also worth mentioning is projection effects, which is essentially the wider that your bin is, the more it kind of washes out your large scale structure, which is shown here. This is a plot from Awan and Gweiser 2020, where on the left side, it shows essentially the true underlying matter density distribution. And on the right side, it shows the same matter density distribution for a wider redshift range. And you can see it's much less distinct there. And that's essentially that projection effect that you're averaging now over a larger radial distance. All right, so here you can actually see what the improvements are to the N of Z's for these bins. This shows for 8 bins when using the neural network classifier. So this left panel here shows these same plots that I've been showing for the past couple of slides, but this is the distribution just after the initial TPZ fit. And on the right side shows the distribution after using a neural network classifier cut of 0.8. And you can see that, especially if you look at the bottom edges of each of these bins, like this orange bin has a much smaller tail and essentially no presence in distant bins, as opposed to here, where you can see that it has at least a small fraction of the objects in that orange bin get actually distributed to higher bins. We can plot the total contamination fraction as a function of the neural network confidence. And here, each of these curves corresponds to a different number of tomographic bins. So going from 4 at the bottom up to 12 at the top. And the interesting thing here is that all of these curves are more or less parallel. So essentially, the neural network classifier can improve the contamination fraction, the total contamination fraction, by a relatively constant amount, regardless of your number of bins that you have, which is going to be beneficial for our cosmological signal to noise measurements. All right, and here is the big important plot. So this is the total signal to noise from the galaxy angular power spectra as a function of the neural network confidence value. And I've maximized the number of bins that you can have with the constraint that the contamination fraction has to stay less than 0.3. And so essentially this produces a curve here where I put a diamond at the beginning and the end so you can see what the tails look like. but I plotted the point that is the maximum signal to noise for that particular number of bins with this constraint. And you can see here that it actually does provide a reasonable improvement to the signal to noise ratio, and it optimizes at about 8 bins. So this isn't necessarily meant for us to be a true measurement of the signal to noise. We did essentially a quick calculation using the core cosmology library from Desk to just see what improvement is there. Is there an improvement? And we can see that as our number of bins go up, our signal to noise goes up as expected, but then it drops off precipitously once you start running into the shot noise limit.
So this is very specifically, as I understand it, a statement about the HSC data set going down to 25th magnitude. So that is, you're assuming a specific depth of the survey in those particular photometric bands. Am I saying that
Yes.
correct? I mean, I'm asking this question with the back of my mind, Rubin Observatory, which will go a magnitude deeper and have
Yes.
another band, where I imagine you may want to rethink or redo this.
Oh yeah, so yeah, this is really meant to be just an example of the improvement possible, but in reality, you would want to probably do some higher dimensional fit to really like optimize what the real number of bins used that you want and all that stuff. But yeah. All right, so I'll go ahead and leave my conclusions here, but before I go to questions, I do want to point out that this second to last data point, or the second to last bullet here, which is the paper was recently accepted by AppJ. It's now on the archive, so feel free to look it up. And also, the future steps for this work are that it is being applied to the Desk Tomographic Challenge, which was a challenge where groups were invited to essentially assign galaxies to different redshift bins in an effort to just maximize the 3x2 point signal to noise. And so this is essentially being added into the runners by Irene Moskowitz, who's another graduate student in our research group. And she's going to compete it against those essentially best algorithms from that tomographic challenge to see how it fares against them. So thank you very much for your time, and I would be very happy to answer any questions.
Thank you very much, Adam, for a very nice talk.
Shirley's also raised
Yeah,
her hand.
Shirley.
but-
Sorry?
Shirley raised her hand on Zoom.
Okay. Shall we?
Don't worry, I was trying to clap my hands. I'm
Okay, it was just hand clapping. Yes.
Questions? Can you go back to like the case theory based for selection function?
Was it like this slide or?
These ones, yeah. So there's usually these like weird striations that's, I guess get reduced as you go to the NNC selection.
Yeah.
They're still like pretty present there.
Mhm.
Like, is that to be interpreted as like the cuts have a weird selection over like different redshifts? If there's some redshifts where it's cutting off a large amount of the outliers and some redshifts that's cutting off not that many outliers.
So I think there are two explanations for that. One is that you'll notice that those bands also occur at where it's a little bit hard to see on this monitor, but where there's a particularly dark region on here. So that's an over density in Cosmos 2015, which will naturally produce a wider distribution on the resultant plots. But also those could be galaxies that just have blue spectra that they, like a spectroscopic redshift could pick up on what their redshift is, but their photoz's get hung up on some particular redshift kind of thing. So
can you go to ridiculous case 3 for a sec?
Mhm.
Maybe also start-
yeah, so this one actually has really bad banding, as you can see. Yeah, but I think a lot of that is really due to just these over densities. In Cosmos 2015.
Because it happens with Cosmos ones, but then happen with the HSC ones.
Right, and I think that's why that's the case. Yeah. Yes, sir.
You go first.
I have two questions.
Okay.
First one is, So the feature space that you use is the redshift predictions from the TPZ, and then the magnitudes, the colors, and the band triplets.
Yep.
Isn't that information a little bit redundant?
Yes, it is.
And do you use that because it actually helps?
So that's a great question. If you there's an appendix in my paper about this, where we basically looked at. It's not uncommon to use magnitudes and colors. Obviously, this was kind of the new hip thing is the band triplets. We did analysis using them and not using them as features, and we found that there really wasn't that big of a difference in the results. So we left them in because we just didn't. We weren't computationally limited, so there was no problem with leaving them in. But you're correct when you say that they are redundant, and I think probably the thing that's on your mind is that neural networks are typically pretty good at making linear combinations of features, and that is true, but it has some caveats, which is that before you train a neural network, you have to whiten the data. So you're going to take each individual feature, make its mean 0 and variance 1. So that's going to actually remove a lot of the connections between your adjacent bands, right? And it is true that the neural network could actually learn those connections and re-stitch them back together as part of its fitting process, but that's going to take essentially 1 neuron per feature, and you're adding work for your neural network, which is is not worth it. So if you have features, even if they're linear combinations of other features that you think are physically meaningful, you can improve the training of your neural network by including them as features anyway, is really the moral of the story.
So I have another question, which is, how are you, so I'm not sure I understand this procedure of classifying the redshift, photometric redshifts, rather than simply improving the photo Z's.
Okay.
Like, aren't you in a way just supplementing the training data of the TPZ with now your new data? Because you're not adding any extra information. You're just taking the output of the neural network. It's like literally adding extra layers.
Yeah. So I wouldn't say that we don't have any new information, because if we didn't have any new information, then our results would essentially lie on top of these black and gray curves here, because we weren't able to extract anything additional out of the data, basically. Because this is essentially TPZ's best estimate of which galaxies have the best and worst redshifts, right?
Right. I guess I mean, like, you're not extracting any extra data from your training set plus the TPZ training set. So if you were to train Photo Z code with both data sets, wouldn't you do just as well?
So I think I know what you're asking, which is one of the things that we attempted in the course of this analysis was adding a third intermediary step, where we would start with a Photo Z fit by TPZ, and then we would run that through a neural network regressor, which would attempt to correct the TPZ fit. And then we would put that through a classifier, where it would say, is the neural network regressor corrected Photo Z better, or is the TPZ Photo Z better? And again, we found that actually was, it didn't improve the results actually to try and regress for the difference between the true redshift and the Photo Z. But it was able to recognize galaxies with more reliability than TPZ that had accurate redshifts. So I hope that answers your question.
Andrew's got a question, and then Shirley's also got a question.
Oh, okay.
No, Andrew.
Okay. Yeah. So you focused mostly on these relatively simple statistics in this true redshift Photo Z 2D space, and it's of course sensible, I guess, to have that, to have a nice linear relation too. But you want to do several cosmological analyses with these data. Would it make sense to take into account the cosmology that you want to do Because you kind of, I could imagine some project cares more about this redshift range and another cares more. So some project could, you know, could swallow some uncertainty here, but really wants this part.
I see what you mean,
separate.
yeah.
Is that doable, or is it too expensive, or is this good enough for everything?
So I think that's very doable, actually. The neural network training portion of this is actually very fast, which is compared to TPZ running, which typically raises some eyebrows. But I think that it's just because TPZ is kind of this custom coded, it doesn't have a scikit-learn backend. It's a custom coded random forest algorithm. But yeah, so the neural network training of this is actually quite fast. And so if you wanted to select down to your particular redshift range and do a training set there or something, I think that's very doable. I ran everything on my laptop. So this wasn't done on some computing cluster somewhere else. It's very, very accessible. Yeah. Shirley?
Hey, I hope I don't sound too loud. I know how it works sometimes in the Zoom. Two questions. One is technical, which I'll go first, which is when we train neural network, very often when we add noise to the data, it would actually generalize better and actually test better instead of, you know, you will have like worse validation noise, but you actually have better test noise. So that's something I wonder if you guys have tried. And then the second question is much more, you know, cosmology related. Is, you know, you hinted at, given that Vera Rubin will have a huge number of photometric redshifts and all these, you know, data sets, that you can actually have very large number of tomographic redshift bands. And I wonder, when you say very large, like what do you envision, and do you have a sense of it? Thank you.
Mm-hmm. Okay, so to answer your first question, we did not add noise to the training sets for the first 3 cases. Those were just meant to be, those are learning exercises that kind of build up an intuition for how our method behaves on different combinations of training and test sets. But for this 4th case, where we actually constructed the training sample, we would essentially add noise such that the uncertainties in each particular photometric redshift, or sorry, each photometric band matched that of the validation object it was matched to. So in that case, essentially the noise between the training and test sets should be really nearly identical. Let me think. Your second point was on the number of photometric redshift bins for LSST. Is that what it was? So obviously for our, where'd it go? There it is. For our test case, we came out with an optimal number of bins of 8 bins, but I think that really it would require a much more thorough analysis to be able to say what the new normal might look like when using this analysis. So I could envision a more multivariate fit where you're kind of optimizing over the allowed contamination fraction and the number of bins and the neural network confidence value to kind of get some global maximum, and that would really kind of solidify what the maximum number of redshift bins allowable is. So you can take this as an example case, but I don't know that I have an estimate of what I think the typical case would look like if we did this over many iterations. So.
So let me ask a version of a question I'd asked before, which is, you are selecting or rejecting galaxies in certain regions of physical property space.
Mm-hmm.
And so for cosmology, at least for weak lensing, that may be okay, but for if you're looking at galaxies that have different bias properties or other things, you have looking at a bias subset of the bias galaxies.
Yeah, yeah.
And So have you thought about sort of the pros and cons I mean, there must be, there are scientific problems for which this is probably not the right way to go, and others for which it very much is. I wonder if you could discuss that a little bit.
Yeah, so as I showed earlier, obviously the distribution in Redshift even is not very uniform, but it was good enough for our case. And in terms of the bias, that I feel like the bias is always kind of the boogeyman of kind of these galaxy selection things, right? It's just that you never know if your bias is biased, but I think that as it stands right now, I think this method fits with our current best estimates of the bias, like our uncertainties on that it's not going to be I think if it biases the sample, it's going to be within measurement uncertainties of the bias already. But I do think that is something to consider as our measurements of the bias improve, that we'll need to, verify these sorts of methods to make sure that they're not biasing our galaxy bias in the sample. I don't know if I can come up with an example case where this would be a poor choice, because I mean, I envision that while this is optimized for cosmology, that we want to have some redshifts, some sample of galaxies with accurate redshifts, I think that you could actually use this also for looking at galaxy properties or whatever it might be, because the redshift is so integral to understanding physical properties of galaxies that if you wanted to do some, statistical representation of a galaxy population in any physical parameter, that something like this might be helpful as well. So, but you do run into those same sorts of selection issues. So, yeah, it's hard to say. I think looking at the cuts in your feature space that it makes, kind of like you mentioned, of looking at the color magnitude distributions for different cuts of the neural network classifier would be instructive in those cases.